Welcome back to Signals and Systems series of videos. In this particular video, we are starting to have a conversation about the various form and tools and transforms that are available to us to be able to look at a signal both in time domain. Of course, you know what domain means the horizontal axis is time in the case of a time domain, and in the case of a frequency domain, it means frequency is the horizontal axis we plot things or think about things. So our goal here is to give us these tools where we can take any signal, any system, and start thinking about them in terms of time when it's convenient and in terms of frequency when it's convenient. So we're going to start our first conversation with one of the basic building blocks of everything else we're going to talk about, and that basic building block is referred to here as written as e to the j omega t, and this signal is referred to as a continuous time complex exponential signal. And then later on we'll come back and talk about LTI, system response, which we usually show that as h of t. But before we go too far, we need to understand what this continuous time exponential signal really is. And in order for us to understand that, you have to remember from our earlier conversation the concept that we introduced, the set of identities we introduced called Euler's Identity. Now, if you plan to, hopefully you are, to really understand the material we're going to cover from here forward in almost all the other videos that have in this section, it's really important for everyone to be very, very comfortable with what these Euler's identities really are. That basically says that e to the j anything alpha is equal to cosine of alpha plus j sine of alpha. Okay, and actually we can write this both for plus and minus, and I will use a different one just to, so you can either this be a plus or this could be a minus. So you could have e to the j, j plus j alpha, or you can have it as minus j alpha. If it's plus, this would be plus. If it's minus, that will be minus. It's as simple as that. So this is an important one called Euler's Identity. And what I'm going to do, I'm going to go ahead and erase this and write it a little cleaner so you can kind of see it. So if you've got e to the j, okay, alpha, if it's going to be either plus or minus. If it's plus, then this will be a plus here. If it's a minus, it will be here. Now, simply by taking these and move them around, we can come up with the opposite. So we can go from a sine or a cosine to e to the j omega. And simply what we're doing, we're either adding, if we go ahead and add e to the j alpha, actually better yet, I could write it, this is probably the better way of writing it, saying cosine of alpha is equal to e to the j alpha plus e to the minus j alpha divided by 2. Because if you look at this, will be cosine plus j sine. This will be cosine minus j. So cosines cancel each other out. You end up with 2 cosine divided by 2. You got a cosine. You can also, if you like, write the sign for this. So sine of alpha would be, if I subtract it, just the same as the equation there, if I just subtracted j to the alpha minus alpha from e to the j alpha, but this time I have to divide it by 2j. Okay, so once again, these are very, very special relationships, very important. So it's highly, highly recommend either write them in a note and have it always with you, and get to a place you're going to keep applying, because you're going to eventually get to a place where you would know it by heart. The sooner the better. Okay, so if somebody asks you what is this signal here, e to the j omega alpha, your first thing is you say, hey, this is a complex number, and it says, okay, what does it look like in frequency domain? So when we're thinking frequency domain, we're going to always look at that. And all this means, if I'm in a frequency domain where this is omega, all this means, and let's say what the signal, somebody says the signal is, let's put some numbers on it, 5 e to the j omega 0 t, some specific number. Then you say, oh, that's all it means. It means that on an omega scale, wherever omega 0 happens, I have a signal of magnitude 5. Okay? Then they say, okay, what is it in time domain? You say, oh, in time domain, what I have to do, if you want me to do it in time domain, I have to take this thing and I got to rewrite it in terms of sine and cosine. So this thing is cosine omega 0 t plus j sine omega 0 t. Then you have to answer the question, okay, do you want me, this is a complex number now in time domain, so what do you want me to represent here for you if you want me to in time domain? Well, you could say, okay, this signal is, let's say, I don't know, we just make it up, x of t. So this would be x of t in frequency domain, that's what it looked like. So in time domain, what does that look like? You say, well, it's a complex number. I cannot graph it in a two-dimensional world because I can either represent it as a real and imaginary, or I can go into polar form and represent it as a magnitude and phase. Whatever you want can be done. So let's say if you want it in the real, then the real portion of it, for example, would be a cosine. So if this is 0, it would look like boom, boom. And what would be the period? The period for this thing would be, we know that it's omega is equal to 2 pi over t. Therefore, we know that the t for this thing is going to be omega 0 divided by 2 pi. Okay, so this is kind of a fundamental concept we should make sure we are comfortable with. There's a set of identities called Euler identities, which allows us to go from e to the j omega to sine cosine. Then e to the j omega is very special because e to the j omega t tells us whatever the magnitude it has is the magnitude at that particular frequency. So let's take this to the next step and see if we can all agree for some signal. Let's take a example and say, all right, now somebody's telling us to tell them we could draw something simple like cosine of 2000 pi t. Okay, let's put a number in there so it's not boring. 2. I'm overusing 2. Let's call it this one. Oops. Let's be exciting. I call it 3, so we have different numbers in here. So draw this in frequency domain and time domain. So you want 2 drawings, one in time, one in frequency. So the time is really easy. The time, all it is that I have to figure out what the period for this is. Well, I know omega for this thing, or omega 0, and this omega for this one is 2000 pi. And I know that this is equal to 2 pi over period, which means my period for this thing is simply going to be 1 over 1000 or 1 millisecond. Pretty easy. So you say, okay, how do I plot this thing? You say, fine, to plot it, t is going to be here, and I'm going to have a cosine signal. So it starts up here, goes down, back, up, down, on and on. And a period will be from here to here, so this period will be 1 millisecond. What would be the magnitude? The magnitude would be the 3 right here. We are all set. Everything is good to go. So we got the time domain. Now the question is, what is the frequency domain? So, okay, that means I got to figure out what the coefficients of this various e to the j omega is going to be, because that's what tells me what the frequency is. So what you're going to do is all you're going to do, well, later on we'll learn about this concept called Fourier series, but for now we're just going to rely, because this is such a simple signal, this cosine of something, so we can just simply look over here and say, is there any way for my cosine to turn into e to the j omega? And the answer is sure we can. So what we can do is go ahead and grab this signal that we are trying to do, and we're going to take it and we're going to rewrite that signal as 3 times e to the 2000 pi t plus e to the minus 2000 pi t. Again, we're leveraging this Euler's identity divided by 2. Okay, so what are we saying here? So we're saying that now our signal is going to be 3/2 or 1.5 e to the j 2000 pi t plus 3/2 e to the minus 2000 pi t, which, remember, this is just telling you what the frequency is, and this is telling you what the magnitude at that frequency is. So when you plot this thing, you will have omega here, and you're going to have 0 here and here. So you're going to, one frequency is going to be 2000 plus 2000 pi, and the other frequency is going to be minus 2000 pi. So, and then what would be the magnitude? Well, the magnitude would be 3/2 this way, and it would be 3/2 here. Now, what we've done is we've taken our signal that was given right here, we represented it in time domain, and we've represented it in frequency domain. So that was great, all right? But it's kind of nice because it was a cosine, and the Euler identities nicely allowed us to take the cosine or the sine. If it was sine, we could do it too, and turn it into its frequency things, which basically says we got two content, one is plus 2000, one is minus 2000, and what is the minus frequency, we'll deal with that later. But for now, it's all it's representing. If you got a sine, you got two components on two sides of the zero running at 2000 pi. Okay, so now that we've kind of got a handle on what that is, let's go ahead and take a look at some more. So a lot of the work we're gonna right now is gonna feel like I'm arbitrarily doing this, but over time, this would be helpful as we look at different techniques. A lot of the work we do now will leverage, as long as we all agree that we're going to call S, we're going to name S J omega. Okay? And that means that we were able to write, instead of writing e to the j omega t, now we can write e s t. Okay? And so that's great. That's great. Now let's go ahead and see if we are able to figure some stuff out now that we've kind of learned this stuff. And the next step is, remember when we had a function, when we had a system, and that system, that was an LTI system, of course, with the h of t in here, the impulse transfer function, impulse response, and then we had an x coming in here. Okay, we got to make it really simple and say our input is always a to the st, and remember what that is e to the j omega t, so it's a simple exponential or complex exponential signal. And then what comes out of here, we will claim it's actually, it would be nice if we could represent y of t simply as h of s, so magical h of s, we haven't told you what it is, times e to the st. So that would tell us, ooh, look at this, if I could do this, then somebody gives me an input that is e to the j omega t, and don't forget that we just showed that cosine, sine, and all that stuff is simply just a combination of e to the j omega t or est, and since this is a linear system, I can take each one of the e to the j omega 2's, run them through, and add the results up, and I'm good to go. So that allows us to solve a lot of problems without having to do what we had to do before this here. Remember, if you want to stay in time domain, let me use a different color so it's a little maybe easier to read. So y of t was what? Was x of t, right? Or I'm going to write it the other way because of some things I want to do. So h of t, I'm going to call this one h of t convoluted with x of t. So far nothing new, is we're just convoluting to get the output. But how could I get an h of t that's going to help me do this, where x of t comes in? I'll just take that x of t multiplied by h of t and get y of t. So here's the thing we're going to do. We say, oh, we remember that the convolution was integral going from minus infinity to infinity of h of tau. Remember, we're moving x according to the way we wrote it. So x of t minus tau d tau. Perfect. Okay. So now that I have that, is there any way I could simplify? Sure enough, I know my x of t is e to the st, which basically says, okay, great. So I can replace this from minus infinity to infinity. And h of tau, I don't know what it is, so I'm going to leave it alone. And then I know this is e to the t minus tau, right? Because I'm going to replace everywhere there's a t in h of t. I'm sorry, in x of t, and every time there's a t, I'm going to replace it with t minus tau. So this is going to be s times d, and then the integral is tau. Now remember, tau is the variable, which means t is a constant, so I can take all of that out of there. So my y of t gets simplified to integral from minus infinity to infinity, h of tau e to the minus s tau d tau, and here is just going to be e to the st comes out. Okay, now remember, we said we'd really like our output to look like that, so great, let's go ahead and set it equal to that. So h of s e to the st, which means e to the st's are the same, so I can cancel them from both ends, and the conclusion becomes that h of s now is equal to integral from minus infinity to infinity of h of tau and e to the minus s tau d tau. So we've got a bit of a nice equation going here. So we are able to take h of t and turn it to h of s. Once we've done that, then, and if your input is just e to the st, we're done. Okay, so that's great, because now anytime you give me an e to the st, I can turn it into h of s. A couple of definitions. We want to spend a lot of time on it, but I just want to make sure you are aware of it. E to the st is referred to as the eigen function, right? And if you remember, that is the input. Okay? And h of s, for any specific value of omega, right? If, let's say, for here, we had two specific value of omega, minus 2000 pi and plus 2000 pi. So for those particular, when you plug those particular values into your h of s, you're going to get the eigenvalue. So h of s for specific values of s of k is called eigen EIGN values. Okay? All right. And then what happens is basically what we're saying, what really is happening is saying that at any given frequency, all you need to do is to take the input, multiply it by the h of s in that frequency, and you got the output. All right. So that brings us kind of to end of this part of the discussion, which all we're doing is kind of introducing a concept. So let's go back and kind of get the essence of it. One is really emphasizing the importance of eigen identity and the fact that you have to remember those things. The other thing which allows us to convert cosine and sines back to e back to that, and also gives us a kind of a framework to move forward, where we are basically saying that this, and remember this is a polar form, so basically the 5 is the magnitude and the frequency is omega. So this literally becomes a way of representing the magnitude of our signal at a given frequency, which we call this whole thing a frequency spectrum. Okay, so this is our frequency domain. Or we can take it to a cosine and sine. If it's complex, then we have to do real and imaginary, and this is actually called the time domain representation. And then later on, we kind of said we use that scale to show the sine and cosine, how you go from time domain to the frequency domain. And then later on, we came down here and we were talking about if my input happened to be just e to the j omega, which we know if we can do that, and this is a linear system, we can combine a whole bunch of e to the st's together and get more signals out of it. Then I can simply run it through h of t, and we're going to be able to come up with this entity of h of s times e to the st to get that. And we kind of found out what h of s has to be to make that work. We had a couple of definitions there, and then for the eigenvalue and the eigenfunction, just for completeness, we covered those. And just one more thing I wanted to do is let's say you have your input, your x of t to the system may not be just 1, but it may be, let's say, a summation of bunch of values a, k, and k could go from anywhere to anywhere do you like it to go, k goes, let's go from minus infinity to infinity, really doesn't matter. E to the s, different omegas t, if that's the x of t, we are running into a function that has an h of t. We can calculate the y of t now very simply, because I know how to get the h of, if I have h of t, then I can find h of s, which means now I can basically say, all right, if you want your output, the output simply is going to be summation of k going from minus infinity to infinity of all the a of k's times h of s's. Okay, now it's important that each h of s be evaluated at wherever that frequency happened to be sitting, and then e to the sk t. Okay, and so that will allow us to basically expand this introduction, the concept we introduced, to a much broader set of signals when they got many frequency content in them. Okay, so that brings us to the end of this presentation regarding the continuous time complex exponential signal and the associated LTI system response in the frequency domain. That's basically what we did.